Hello, working on section 4.2 today, and we're looking at implicit differentiation. We're going to do this in 2 days, so today is day 1, and you can see on the front screen here, items that we're going to look at is mainly just implicit differentiation, and then a little bit on derivatives of a higher order, like finding a second derivative implicitly. So implicit differentiation allows us to find derivatives of functions that are not defined or written explicitly, like y equals 3x squared. We're going to see that intermix of variables and how to deal with taking derivatives of complicated functions. And they may not even be functions of just some equations. All right, your warm-up today is a BC question from the exam, and take a look at it. It says the table above gives values of differentiable functions f and g and of the derivatives at selected values of x. If h of x is equal to f of x times f of g of x, what is the slope of the graph of h at x equals 2? So there's a couple key pieces of information. One, what is the question asking? What is the slope of the graph? And secondly, they define h of x as a composite function f of g of x. So if I wanted to find the slope, I'm going to connect that information to saying, oh, well, I need to take a derivative. And the derivative I want is h prime of 2, right? That's really what I'm after. Now, h of x is defined as f of g of x, which makes this f prime g of x times g prime of x. We know that is our chain rule. We want to evaluate this at 2, so I'm going to say, well then, let's change colors. H prime of 2 is equal to f prime g of 2 times g prime of 2. And now I can use my table to help find these numbers. All right, so h prime of 2 will become f prime. G of 2 is where I want to start. I got to start at the inside. So g of 2 looks like that leads us to -1 times g prime of 2. G prime of 2 gives me 2. So I'm going to go ahead and insert that, substitute it. One more line item, it looks like, to complete this. I would have h prime of 2 is equal to, well, f prime of -1, according to the chart, is it 3 or negative? It is 3 times 2 gives me an answer of 6. So my final answer, h prime of 2 is 6. I'm going to go with D. Right, next. Example of implicitly defined functions. You can see that we've got the intermix of x's and y's. So this would be a little difficult to just solve for y in this case. And that's where implicit differentiation really comes in handy. You can see over here, you've got them listed in your notes, some steps that you'll want to follow. Differentiate both sides of the equation with respect to x. And then we're going to collect all the terms with dy dx on one side. I typically go to the left side. And then I'll factor out that dy dx so that I can solve for dy dx. Let's walk through the steps and see if they ring a bell for you. So first off, I'm encountering the first term. I'm going to take its derivative. And since it's a variable y, it will be power rule. We'll say 2 times 3, I'll get 6y. But then I'll have to chain off and take the derivative of y with respect to x. So I'll get that dy dx. Plus, derivative of 2y would be 2, and then the derivative of y would be dy dx equals 5x, and the derivative of 5x with respect to x would just be 5 dx, but we know how that simplifies to just 1. So I'm going to let that go off. Now, I'm going to collect the terms with dy dx on one side, and I look at my equation, it's already done. So perfect, we don't have to, we've done that step, it was kind of done for us. Now I'm going to factor out the dy dx. They do have a dy dx in common, we can clearly see that, so let's go ahead and factor that out. So dy dx, and leaves me a 6y plus 2 equals 5. And now for the final step, let's solve for dy dx. And that's simply going to be a division step. So dy dx equals 5 over the grouping that's coming over through division, 6y plus 2. Okay. This is an interesting video that you will hear in class, and it talks about tangent lines and our eyes and how light enters our eye. So it says, in the law that describes how light changes direction as it enters a lens, the important angles are the angles the light makes with the line perpendicular to the surface of the lens at the entry point. That line is called the normal to the surface at the point of entry. In a profile view of the lens, the normal is the line perpendicular to the tangent line that falls tangent to the profile curve at the point of entry. So if this were my point of entry, you can see how the line in red is the tangent line, and then you can create then that normal line that runs perpendicular to the tangent line, and that would represent how that light is going to enter the lens. Okay? At that point, I guess it is. And the other diagram that's kind of interesting is this one, and it has a parabola, which we're familiar with from Algebra 2. Here's that parabola. And then they talk about, in the parabola, remember there was a focus point, there's the vertex, and then you had your directrix line, and the latus rectum was the distance from the focus to the parabola. All those things fall into place with our eyes. I think that's interesting. All right, let's move on to question number 2, example 2. In the xy plane, what is the slope of the tangent line of the line tangent to the graph of x squared plus xy plus y squared equals 7, and then they give us the point. So kind of key piece is what is the slope of the tangent line, and we know how to do that. That means we need to take a derivative. In this case, the derivative will have to be done using implicit differentiation. All right, so sometimes now on the A, B, and BC test, they will tell you what the answer will be, and they'll say, find dy dx, or prove that dy dx is equal to so-and-so, so that they would actually give you the answer to this question, mainly so that you can move on throughout the problem. But we're going to show then how to get to that answer using implicit differentiation. This one has the point given at 2, 1. Let's begin. So I'm going to have 2x. This is going to require a product rule because it is the product of two things. And I take the derivative of the first, which is 1 times the second is y, plus the derivative of the second times the first, so I'd end up with an x dy dx. Because the derivative of y would turn out to be 1 times dy dx. Plus the derivative of y squared, power rule says 2y, and then delve one step in, and we have the derivative of y, which is dy dx, equals the derivative of a constant we know to be 0. Second step, we want to get dy dx on one side, everything else over to the other. So I am going to keep my dy dx on the left side, and I'm going to factor it at the same time, which I'm sure you probably got familiar with doing when you're working in AB. It just saves you a little bit of space and a little bit of time. So I kind of did 2 steps in one. I separated stuff, and I kept the dy dx GCF out front. Now, finally, let's solve for dy dx through division, and I get that. And we had a point, so let's not forget to evaluate. Let's go into evaluation. We are going to evaluate dy dx. How do I show I'm going to evaluate it? Oh, there's notation for that. Of course there is, right? So I'm going to evaluate it at 2, 1. And I'm going to substitute in my values. I'm even going to show, whoops, I did that wrong. I'm going to show that substitution, mainly so that I don't do it wrong, in my head. And I'm going to have an x plus 2 times a 1 for y there. That looks fine. I'm just double checking, make sure I didn't do a copy error. Now I'd have negative 5 over 4. There's my answer. And I'm just going to rewrite the left side and have my answer. Alrighty, moving on to the next question. The slope of the line tangent to the curve at 2, negative 1 is, well, give this one a try yourself. Maybe pause, do some work on your own, and then come back and follow through with me. All right, here we go. I'm going to go 2y dy dx. The next one is a chain rule. Power first, because it's the outer function. So a power of 3 drops to a power of 2. Chain off, now I take the derivative of the inside piece. I hit a product rule, don't I? And the derivative of x is 1 times y plus the derivative of the second, which is dy dx, multiplied by the first. And then I would take the derivative of 1, which is going to turn out to be 0. So I'm going to just close my parenthesis. And the derivative of a number is 0. So even the derivative of 0 is 0. Next, we want to try and sort out things. Can I keep the terms of dy dx on the left side and move everything else over? Not real easily, can I? So in this case, since we are just trying to find a numeric value for the derivative, I'm going to use that point and substitute right now so I can get rid of variables and just make the math a little bit cleaner for myself. So let's substitute in 2, 1. So, or 2, negative 1. I'd have 2 times negative 1 would give me negative 2 dy dx plus 3. X times y would be negative 2 plus 1. Negative 2 plus 1 would be negative 1 getting squared. Y is negative 1 plus x is 2 dy dx. All equals 0. So some of them I simplified, some of them I still wrote down because I just want to take it slowly. That gives me negative 2 dy dx. Negative 1 squared would be a 1 times 3, so I'd have plus 3 times negative 1 plus 2 dy dx equals 0. And one more pass, just keep simplifying step by step. You're fast writers by now, so writing all these extra lines, not a big deal. All right, now I can get my dy dx on one side, my number on the other, so I'm going to move the 3 over. The negative 3 will come over as a positive 3 to the right. Negative 2 plus 6 gives me 4 dy dx, and I'm going to have dy dx equals 3/4. This was evaluated at a point, and it was 2, negative 1. So I'm going to include that information with that evaluation symbol. All right. That was a fun one. Just showing you that you can, if you're really going after a numeric derivative, you can substitute that point earlier on. So even in that previous problem to that one, we could have, once we did this step, we could have brought these numbers in rather than working with variables like I did. So it shows you 2 different approaches to the problem. Keep that tucked away, because that's kind of good to do. All right, finally, we're on the last problem, and it is a second derivative problem. So we're going into the higher order derivatives, and that'll be fun. So in order to get second derivative, we all know that we must get through the first derivative. So let's go after our first derivative. And that's going to be 2x plus 2y dy dx equaling 0. Solve for dy dx, and I'd end up with 2y dy dx equals negative 2x dy dx equals negative 2x divided by 2y. So I get dy dx equals negative x over y. All right, I'm just going to kind of highlight that answer because now I need to pick up from there to go forward into second derivative. So we're going to go into second derivative. It will still be an implicit differentiation. Remember how to do your notation for second derivative. Looks like that. And now we're going to use quotient rule, right? Quotient rule comes into play on this one. All right, derivative of the top would be -1 multiplied by the bottom, which is y. Subtract derivative of the bottom is dy dx. Notice I just moved over because I'm going to put the top in front of it. So I've got derivative of the bottom times the top, all over bottom squared. And it's looking really nice right now. Let's simplify. So I get second derivative equals -y plus x dy dx over y squared. And if you let this be your final answer, allow this as your final answer for the AB or the BC test, you would lose some points because they want the answer to be in terms of x and y. And we know right now we're sitting with a dy dx, aren't we? So since it's a general derivative and not at a point, I am stuck with substituting negative x over y for dy dx. All right, let's proceed. I'm going to change my color just to show this part where we're going to start doing some substituting. So I get second derivative equals -y plus x, substitute -xy for dy dx all over y squared. Now, how do I simplify this? Because now you've got a complex fraction. You have fraction within a fraction. And that's not so cool. We shouldn't leave our answer like that. I would have negative x squared over y over a y squared. Well, what I would really love is to have a denominator there. You can't see that very well. I'd love to have a denominator underneath this one that matches that. Can I do that? Well, for sure. I'll multiply this by a y over a y. Now I have y's for denominators in the top. Let me extend. All right. Here we go. We are so close to done. Y squared, negative y squared, minus x squared over y squared. Well, that's like this, isn't it? If some of you have trouble doing that, just generate that fraction. We know dividing by a fraction is like multiplying by its reciprocal. So I get negative y squared minus x squared over, this would turn into 1 over y squared. So y squared times y gives me y cubed. That is a pretty nice answer, but would you believe it could actually get a little bit better? What I noticed is if I factored out a negative and changed the order, I know what x squared plus y squared is, and you do too. Look back to the original problem, and right here, we have that x squared plus y squared is 25. So I really could take this down to substitute that out with a 25. This will be negative 25 over y cubed is the second derivative. So now you saw another little twist to second derivative problems where you do a little more substituting. Just things to be alert to because it can happen. All right, I think that's it. I will find, I think that is your homework. This homework page, it contains a lot of the AP questions, so gives you a good taste of what implicit differentiation looks like on the exam. Have a good day.